So yeah, I'm Eric Driver. I come from the United States, state of Arizona. Some of the research I do is based in Arizona State University, the math department, obviously. So I will be talking about a number of fields database, and in particular, the part that I work with, which is number fields at home. It's a distributed computing project. So this is a volunteer distributed computing project that I put the URL here in case anybody wants to go there and see what it's about. It uses what's called BOINC. That stands for Berkeley Open Infrastructure for Network Computing. We use that for the distributed computing portion. And then for the number field computations, of course, we use Perry, which is why I'm here. This project is being used to construct it's to help construct number field database. It's primarily concerned with degree 10 fields, which are very computationally intensive, which is why we use distributed computing. The actual number field database contains fields of all degrees up to 11, so it's really big, and the distributed part is just degree 10. So I'll start by discussing the actual database. At the top there, you'll see the URL, how to get there. So it's web-based. It's based on a paper by Jones and Roberts, and I cite that right there if you want to get some of the details of it. They talk about certain completion issues. And then here's a snapshot of what it actually looks like. And you can, so when you search the database, you can put in like the degree of the field you're interested in. You can put in signature, R1 and R2. You can give it an absolute discriminant, a root discriminant that you're interested in, a Galois root discriminant. You can put in the Galois field, the class number, the number of ramified primes, a minimum and a maximum ramified prime. And then you can also specify a list of specific primes and the powers on those primes if you're interested in a very specific ramification structure. And then of course you can give the order that you sort and some other stuff here like the maximum number of fields per page. So I mainly work in the distributed part. I don't really manage this database, so I don't know too much more about it. And it's been many months since I've actually used this, but if there's time at the end, we can maybe try to search for some fields if people are interested. Okay, so I'm going to talk now about the actual number fields at home. It focuses on imprimitive decies. By decies, we mean degree 10 polynomials. And we're interested in ones that have a quadratic subfield. So that means degree 5 extensions of a quadratic. You can also do quadratic extensions of a quintic, but those are much easier, and you don't actually need a distributed computing system. With that said, we actually have tabulated a bunch of those fields having a quintic subfield, and they're in the database. Something we have not done yet are the primitive fields, degree 10 fields. I don't know if anybody has yet. That would obviously be what's called a hunter search. I don't know how familiar people are with that, but that, like I said, has not been attempted. We're assuming it's probably pretty hard and would probably also require distributed computing if it were to be done. And if we have time after the search we're doing now, currently, then we'll maybe attempt that. This project has two primary objectives. The first one is minimum discriminant decies fields. We are using a bound of 1.2 times 10 to the 11th. I think everyone knows what that means, right? You pick a discriminant bound and you want all fields that are less than that bound. We did a search earlier for minimum discriminant decucs, and I think we used a bound of either 10 to the 9th or 10 to the 10th, so it's a much easier search. And we completed that search pretty quickly and filled out a bunch of minimum degree 10 fields in that table. There's a website by Kluner. I'm not sure if anybody's familiar with that. And he has a bunch of minimum discriminant fields, but they're not necessarily guaranteed to be minimum. At least as of a couple years ago, they weren't. So he just has the minimum that they know of. This, when it finds the minimums, are actually guaranteed to be the minimum. And one reason we chose this particular bound here is it will encompass some more fields that are in his table that were not in our original search. And so it'll at least prove that those are indeed the minimum discriminants. A second objective are decuc fields that are unramified outside a particular set of primes. So what that means is it's ramified at primes in S, but it can be either or, right? It doesn't have to be every prime in the set. So for that search, so far we've completed all single primes up to 47. We've completed all prime pairs, or not all prime pairs, but these prime pairs here, 2, 3, 3, 7, 3, 11, and 7, 11, and those are complete. We are currently processing the 2, 5 case, which, because of the fact that these are degree 10 and you're dividing by both 2 and 5, you have wild ramification, and your discriminant bounds get extremely large, and so this is a very computationally intensive task, and it's currently been working for about 2 years. There are, so if you consider the set 2, 5, there are 7 quadratic subfields that are ramified at either 2, 5, or both 2 and 5. And so what you do is you do a search for each of those quadratic fields. And so far we've done the first 2, and we are currently on the 3rd one. So I wanted to say a few words about BOINC in case nobody was familiar with this. I think I said earlier, it stands for Berkeley Open Infrastructure for Network Computing. It's open source code, which means anybody with a computer and an IP address can create a work server. The reason that that's important is if you have a very low budget, you can get a lot of computational power with very few dollars, because it's all volunteer computing. So you may be familiar with some of these famous distributed computing projects. There's the Great Internet Mersenne Prime Search, otherwise known as GIMPS, and then there's SETI, the Search for Extraterrestrial Intelligence. Now actually GIMPS used a different system. It wasn't based on BOINC, but it used a kind of a similar type process. I don't know if it was open source though. And then I just wanted to give you some stats on the number fields at home project, just to give you an idea of what kind of processing power you can get. Currently we have over 5,000 users. Among those users, there are over 19,000 host computers. Recently, as of 2 weeks ago when I checked, it was at 12 teraflops. Recently, I checked last night, it was over 13. So the number of teraflops fluctuates with the users, right? Users log in, they'll log back out, so it fluctuates. But for a few months now, we've actually been over 12 teraflops, which is pretty good. That is equivalent approximately to a 6,000 core supercomputer. So if you can imagine how much one of those, it would be millions of dollars to pay for that kind of supercomputer. So like I said, if you have a very small budget and you need a lot of processing power, this is the way to go. The first time I did this, it only took me 2 weeks to get it all up and running. So you could even hire somebody to do this and do the maintenance on it, and that's still a lot less expensive than actually purchasing a supercomputer. So something to keep in mind if one day you guys are ever doing something that you need a lot of power, this is the way to go. So the last thing I wanted to discuss is I had been asked how either some of the stuff I've done here can benefit Perry or the other way around. If there can be a change to Perry that can benefit this project. So I gave it some thought. And Bill, we could talk about this more offline if you want afterwards. But most of what I have here, a lot of the code I have is the standard Hunter and Martinet type searches, which as far as I know, I haven't looked through deep in the Perry code far enough, but I don't believe anything like that is in the actual Perry code base. But I do have code there that could be converted into Perry libraries. Again, I don't know how useful that would be, because most of these fields that you would get are in a database anyways, so you could just go to a database and get them. So something to talk about if that's something that would be useful. I also have code for the higher degree searches, up to degree 10. Once you get above 8, it takes a lot of computational power, so you may not, I don't know if it'd be nice to have that as a library function in Perry, because a single user with a single thread would be taking a lot of time to do calculations. And again, they're in a database. So something we can talk about if people are interested. I also have code that is more particular to doing what we call targeted ramification. So this is where you're not just looking at all fields with some discriminant, but you're targeting a very specific ramification structure. The searches I do here, it's searching over all possible ramification structures for the primes that you choose. If you could pick just the one particular ramification structure, and that might be something that would be doable, because then it's not as big of a search, it's more of a smaller search, or maybe a particular thing you're searching for. That might be useful. That's about all I have to talk about. We could, if people are interested, take a look at the database and just see how that works. Would that be helpful? Okay. Let me just pull up an internet browser. Before I continue, are there any questions?
I have a comment. It's very useful that you have Hunter and Martinez subroutine, because okay, there are databases that have been published, but at least for the old databases, all the code that generates the database was lost mostly, and so very few people, we could not really prove that the database were corrected. And yes, and experts have some good reason to believe that maybe they could be correct, but by chance. No, I mean, well, you are looking about a billion of candidates. So if you make one mistake, if it happens not for a solution, you won't notice it. So you can make a lot of error without ever notice that you have the wrong result. But it's not mathematically satisfying because it's not a proof. I mean, so it seems very useful. Even if the database are published, it's very useful to have code that you can say. If you have, you can say, okay, but this database was there is this code, and you can check the code and see whether you think it's correct or not.
Another thing that reminds me of is during these searches that have been running for years now, I think it's searched over many trillions of polynomials using all the number field, NFDisk, PaulDisk, PaulRedAbs, all those Perry functions, which has really stressed the Perry code. And there's only been a couple of seg faults here and there. So it's very, very well-written code. And every time that happens, I pass it to Bill, and he figures out the problem.
Question.
Oh, yes.
I mean, at this point, you say that you have a strict list of with the prime 2 and 3, for example.
Yes.
But what does it mean to complete it?
So complete is,
Anderson discriminant or Wisdom rule of discriminant or?
no. So if you fix ramification at only the primes 2 and 3,
Yes.
there's a finite number of fields that are ramified at 2, 3, or 2 and 3. So there's, and then we find all those fields. Yes. Once you pick the ramification. How do I get out of here? Ah, there we go. I need to find the. Oops, it's not there. Do it that way. This works on my computer. Does anybody know how to do a link here? Copy paste? Yeah. Oh, did it? You think it opened?
Oh, yes, it is.
I don't know why it's not working. I'll just copy paste. Yeah, how do I copy this? I normally have a mouse. Oh, what? Oh. I don't know how to. I usually have a mouse.
Try it.
Yeah, do you want to try?
It's more. Also, it's kind of.
Oh, there you go. Okay. So is there anything somebody's interested in looking at, or I can just pick something? Maybe the 2 and 3 for degree 10? Okay. So we'll put degree 10, and then I think, it's been a while since I've done this. I think we just put 2 there.
Now you have this discriminant bounded, I guess.
Yeah, I might have to remove that. Otherwise, yeah, it will. So let's. I'm trying to check it. There we go. So it's searching. And then here are the results. Much better. Thank you. Okay, so these are the results of that search. So there's 1,261 such fields, and it's doing 100 per page. And here they are. That's sorted by the Galois group. And you can just look at them all there. If you wanted them all in one, you could just, on the previous page, you could tell how many to put on a page.
How do you, the computation of the Galois group, is it using the body command?
It did originally. It's not doing it on the fly. It's when it's in the database.
Yeah.
So it's pre-computed and put into the database.
Yeah.
So, but Perry was used
Okay. Yeah.
to do these calculations.
It's like Paul Galois. But maybe you use some kind of parametric families. So then you only test the candidate polynomial that have the right to get a group or.
Yes. So our search turns a ton of polynomials, and then we use the Paul-Read abs to reduce to pseudo-canonical form, and then you remove duplicates. And then what's left, we then compute like class groups and the Galois group and all that stuff, and then puts it back in the database. And then there's a link here for data file, which I believe will return it into a data file structure that you can then use. And I haven't actually tried that in a long time, but we can see what it does. Okay, it puts it in Perry format. You see, the same format, so you can just load it directly into Perry or GP.
If you have very large file, you might want to try the readback format.
Okay.
So you need to put a bracket. The readback format is the function. The readback function just read the file line by line.
Yes.
But all the line is a separate component of a vector. So it has good properties if you have a very large file. Otherwise you need to the GP parser need to read the whole file at once.
Yes.
And so you need a lot of memory. And then to build your vector. So, but if you do read vec, it reads all lines separately, and so it needs much less memory.
Okay. Are there any other questions? That's all I have.
So what? So you are still running your distributed computation?
Yeah, it'll be running for probably years.
And
So after 2.5, we're going to do other cases, and then just keep going.
So I think you said you were looking for the third polynomial, or you say something that you already found two polynomials.
I found two.
Two
Two of the subfields. The two of the quadratic subfields are complete.
Yes.
I can actually show you what I mean. So this is not working. Okay, I'll just. Okay, so this is the distributed computing site. This is where all the users go. So they can check their account, they can look at stuff. And I have a link here to a different format of the data, which is, this is our old way of doing it, where it's actually sorted. I'm not sure if you've seen this. And so you can actually go to DECX with quadratic subfield.
So you recheck out all this database?
These all went into the database. So
But did you personally recheck all this?
I personally have not done the database part. I just did this here. I create this web page with a table.
No, I mean the computation.
Yeah.
You did computation of polynomials.
Yes.
But did you redo this for the lowest?
Yeah, I actually did do these for all the lower. This was part of my dissertation years ago. So they're much easier to do. I could do it on my single computer.
Yeah.
It wasn't.
On the web you can, yes, but at the
Yeah.
time it was done, it was much slower. So it's very useful to have an independent verification of the data.
Mm-hmm. So here at the bottom, you can see the cases where S does contain 2 primes, and it's broken down by Galois group and then by the subfield. So you can see there's 2, 3, all 7 of the quadratic subfields, and then the number of fields for that particular Galois group, and then at the end the total, and then links to the actual data files. And you can see 2.5 only has the 2 of them. So I think I'm right at time.
Yeah.
So thank you.
Any question?